Vancouver-based poet, artist, storyteller, and sometimes philosophy student. His work has been published 9 times in various literary journals, and he performs them live around the Lower Mainland. He also acts as a cameraman for local events and maintains a YouTube channel on this basis. What fictional scientist would JQ want to meet? He says, it would have to be Dr. Horrible. I mean, obvious. All right, come on up, Vicky.
Okay, this is essentially a book review of Thomas Kuhn's The Structure of Scientific Revolutions. The topic is philosophy of science. This piece is called Kuhn's Paradigm. Tonight, I'd like to introduce you to a philosophy of science concept by one of the most quoted names in that field, that being Thomas Kuhn. His primary work, The Structure of Scientific Revolutions, has been labeled by some as the most important book of the 20th century. Published in 1962, it played a large part in establishing philosophy of science as a field of inquiry. Its central concept, that of the paradigm, is what I'll cover now. To quote the author, normal science is predicated on the assumption that scientists know what the world is like. In other words, there exists within the contemporary research community a shared conceptual model, one frequently identified, which guides their research. This model directs both the type of questions the scientists will ask, along with the type of answers considered acceptable. This worldview is what Kuhn refers to as a paradigm. Standard philosophy of science likes to highlight 2 major revolutions in human thought that exemplify significant advances in scientific thinking that constitute a new paradigm of thought. These are the transition from the Ptolemaic model of the solar system to the Copernican model, and the movement from Newtonian mechanics to relativity. There's other examples, but I'm going to focus on these 2 for the sake of economy. In roughly 100 AD, Claudius Ptolemy advanced a model of the solar system, which was mostly a refinement of what his society inherited from the Greeks, one with the Earth at its center. It boasted an unusual success in predicting the motions of the planets to an observer, enough that it became the standard model and remained unchallenged for another 13 centuries. An interesting aside is that modern-day planetariums, with their motorized projectors, use area systems that imitate Ptolemaic motion to project the sky from an earthbound perspective. It was that successful. But in 1543, along comes Nicholas Copernicus, a Polish astronomer who takes issue with some of the irregularities in the Ptolemaic model, particularly growing inaccuracy in its predictions over time. He advances the heliocentric model, one with the sun at the center of the system. This new idea answers many of the former's unresolved technical problems, and of course introduces a whole new set of political ones. Planetary motion, which requires complex behavior such as epicycles, now can be explained just by placing every planet orbiting the sun along with the Earth. A new paradigm for astronomy has been wrought. At first, scientific researchers investigate various topics and perform experiments on whatever issues they think are relevant or interesting. But eventually, one piece of research and the data it collects stand out above the rest. This one appears to shed light on some basic mechanisms of nature and provides grounds for further research. This branch of science has its first paradigm. Now, for another example of the paradigm shift. It's important not to underestimate the fundamental defining power that the scientific paradigm has for the body of research. It isn't just that these 2 scientists see a different picture when they look at the phenomena they're studying, it's that they can't even have a conversation with each other. It wasn't just the shape of the solar system that changed between Ptolemy and Copernicus. Humanity's place in the cosmos underwent a basic transformation. The new brand of astronomer saw himself standing on different ground as he went stargazing. Now for another example. In 1686, Isaac Newton developed supreme laws of motion to further explain the behavior of the planets and physical motion in general. This set of rules meets with immense success and remains without competition until the 20th century. These 3 laws are used by engineers and physicists as well as astronomers to provide a direct route to apply mathematics to observe physical motion. Although physics has undergone 2 complete revolutions since Newton conceived this model, these 3 laws remain as relevant as ever. But in the 19th century, new evidence emerged. There was reasonably accurate determination of the speed of light. More importantly, the famous Michelson-Morley experiment proved that light came from the observer at exactly the same speed regardless of whether you were moving towards or away from it. This conclusion directly violated Newtonian mechanics on a deep level. Albert Einstein comes along and introduces a complete game changer. The idea that time and space might be relative to the observer, not the fixed absolutes that Newton and everyone else had blindly assumed them to be. This preconception was one of those classic unknown knowns, something everyone knew, but they didn't know they knew it. It was an assumption so basic it was never even identified until Einstein challenged it directly. With this framework and a little 10th grade algebra to apply it, an entire revolution in physics happened. Now, marching under the banner of the current paradigm, the researchers have worked to counter phenomena which don't necessarily fit the explanatory framework entirely, or perhaps not at all. Kuhn refers to these counter instances as anomalies. Normal science runs into these anomalies regularly. This is nothing out of the ordinary. But when they accumulate to an exceptional degree, one glaring example that resists explanation by the experts. The practitioners at science begin to lose faith in the dominant paradigm. Then they reach a state of crisis. Several conclusions regarding the role of scientific paradigms can be taken from these examples. Researchers who participate in a shared paradigm share a commitment to the same rules and standards of scientific practice. These paradigms serve to create lines of inquiry regarding problems, and therefore act to articulate the questions through which research begins. They go on to define areas of relevance for research, what we can look at. In the long term, when the paradigm itself becomes an object of scrutiny, it reveals something else about science. That is, that science is itself a cultural practice, one which is historically embedded, just as social theory or political thought is. Scientific research looks like the age in which it is conducted, and that includes the scientific studies being made today. With this bit of historical hindsight, it's reasonable to think that in another 200 years, most of the major scientific models of today will have been superseded, if not abandoned. One can't help but wonder what view they will take of quantum mechanics. They thought, what? The schemes of definition within that generation will be working will likely make many of our current models look like phlogiston theory of combustion or the caloric theory of heat, both accepted models 2 centuries ago. But what's important to remember is that those models provided at least some explanatory value to the scientists at that time, and the same can certainly be said of the theories we use today. The realization that we're working within the paradigms of the present era shouldn't invalidate us in any way. It should merely make us properly wary of any present-day claims of absolute knowledge, both within and without the community of science. Thanks.